up. We are the error mixing station speed operation. We measure the motor output from a certain voltage input. My name is Daniel Kelly. My team is Andy Burke, Trevor Thomas, and Sarah Rogers. First, I want to go through some system backgrounds, talk about the system schematic, what it does, talk about the SSOC, the steady state curve, the graph for what areas it's steady state in and why. We're going to look at the results from our step response experimentally, and then also our modeling results from our equation fit, and then conclusion. This is basically what our system looks like. The input motor power is in percentage of the full range voltage, goes through the mixer drive system, and comes out as a motor RPM speed. It maxes out around 1800. This is our schematic of our system. The SRC is the control board. Basically, you control a voltage output through a gearbox, which goes into a mixer, and then the idea is that it mixes oxygen into wastewater, and those microbes break down the waste into something that's safe to be released into the environment. Our steady state operating curve is almost perfectly linear. So it gets a little bit squirrely below about 5%, and toward 95% when the motor starts to hit overpower a little bit, but generally it's linear. So any input, you can just basically have a standard y equals mx plus b equation to find given output. This is our steady state response curve. The first, we get to our transient behavior ends after about 2.5 seconds. So anything after about 3 seconds can be assured to be steady state. Okay. This is for 55% input power. Thank you. Appreciate that. So we have, this is for, I think this was Trevor's chart. So you can see how flat that curve is after 3 seconds. It's almost like there's no movement at all. This is our, this is a breakdown of our transient steady state curve. So we have our tau is about 0.32 seconds, measured by the 0.632 of the delta C value. K is around 17.5 RPMs gained per degree per percent input. And our T0 is roughly 0.1 seconds for all of our tests. This is the model equation that we used. A is the increase in input gain, and then there's a time function from TD, which all that does is move the graph left to right. And then T0 is the dead time. K is the gain, and tau is our time constant. And then added in is the output balance in RPMs. This is a sample from our, I believe this was for, this is for a 45 to 70% jump. This was one of Sarah's graphs. So as you can see here, this is our model output and input compared to the experimental value, and it's extremely close, almost indistinguishable from each other. Part of that reason is because it's such a good steady state model, and also because we're able to fiddle with the numbers a lot and get them extremely close. So the green is the model output, which is the curve fit to the experimental output, which is blue, and the input and output percentages are in red. This is a step down. Not quite as good of a fit here. A little bit of wiggling on the top even, and then fits a little bit off on the top edge, right where the air forms experimental output. The same thing goes here. The green is model, and then the blue is experimental. This was for the this was for a 45 to 25% drop. Our section was a little bit unique because we also did alternate method thanks to Andy. Basically, what is done here is that A0 is calculated from adding in time times L and T and getting a time constant, much like similar to how, from what I understand, how tau is defined as 0.632. So A is found and then it's put into an equation that's similar to A0 is found, put in an equation similar to what the rest of us did for our time equation. CT equals A plus everything else. And it's measured in revolutions times seconds per minute over the period of the experiment. We use trapezoidal integration, so it's a lot more difficult and a lot more time consuming to do it that way. but there's some interesting things to see later in our data. This is how tau looks. What this is red and blue are step up and step down for the original experimental equation from 2 weeks ago. The yellow and green are the model up and down from the blue. So keep in mind that the 5.5% curve is the one that was for the alternate method. Those are much more accurate and have much less standard deviation between the two of them than any other measurement area. And it doesn't make sense to say that it's just because it's a low speed, which would make sense for a lot of systems, but because it's so linear, they should be similar. So here you can see we have a high standard deviation of 25 to 45% for the model, interestingly much higher than for the experimental. And a lot, both of the medium ones and the high range have quite a bit of difference between the model and the experimental for both up and down, but 5.5% is still very, very consistent. And you also see the same thing through here for our K value. So our K values dropped pretty consistently as speed increased, and they usually average around 17.4 to 17.6. But again, the alternate method, while it takes a lot more time, seems to be a lot more accurate in agreeing with the earlier experimental data. In conclusion, our SOC is extremely linear. The output value for the speed can be easily determined from the input values using SSOC. Our graphic approximation of the first order plus dead time model is extremely accurate. At least results mostly within the uncertainties you guys saw from the bar charts of the experimental values. Also, would add a notation is that the alternate method yields even more accurate results than the modeling that everyone else did.